So our next lecture is on simplifying radicals, and we're going to have some properties similar to the previous section, but now we're going to be simplifying radical expressions. So if I have to take the nth root of a product AB, you can break that up as the nth root of A times the nth root of B. Another property is if you take the nth root of a quotient, you can break that up as the nth root of the numerator divided by the nth root of the denominator. And another really nice useful property is if you take the square root of a real number squared, then that becomes the absolute value of A. The reason for that is while A squared is A, if you take the negative of a number and you square it, if you take negative A and you square that, that would also give you A squared. So a generalization of this is the nth root of A to the n will be, the absolute value of A is if n is even, and it will just be A. You won't have any absolute values if n is odd. So we can use these properties to solve some simplification, similar to what we did before, but this is sort of extra properties that we have and we can use now. So let's try to solve some of these problems. If I take the square root of 32, and you want to simplify that as much as possible, well, there is no number whose square is 32 other than just root 32. Okay, so there's no whole number, is what I mean. So what we could do is our next best simplification is, can you find a number where 32, we can decompose 32 essentially. Okay, I could rewrite 32 as 16 times 2. And the reason I would do that is because 16 is a perfect square, meaning it is a number whose square root is a whole number. So now, look at this. I can use this first property here, and I can decompose that square root as the square root of 16 times the square root of 2. And the square root of 16 we know is 4, because 4 squared is 16. 4 times 4 is 16. But root 2, we're just going to leave that as root 2. We can't decompose that anymore. Root 2 is a number, right? And the square of that is 2. But it's not going to be, we can't decompose that any further. So the idea here is if you get a number and it doesn't happen to be a perfect square, right? It still has a square root, right? But the simplification process is you want to get it to sort of these simplified roots, okay? And if you can find a perfect square proportion out of it, then you can rewrite that. Okay, this will definitely be helpful when we have to combine like terms and many other situations. We're going to use this idea. Okay, so we'd have 4 root 2. Okay, going on to our next example, we want to take the square root of 75. Now 75 isn't a perfect square, but we can factor this, right? So 75, we could factor that as 25 times 3, right? And 25 is a perfect square. So we're going to use that property up here again, property 1. And we have a product, so I can rewrite that as the square root of 25 times the square root of 3. And 25 is a perfect square, and that's 5, right? 5 squared is 25. And root 3, we're not going to be able to simplify that any further, okay? So root 3 is just root 3. Can't factor that any further. The factorization of 3 is just 3 and 1. What about 27? Now 27 is actually a perfect cube because 3 cubed is 27, but it's not a perfect square. Okay, there isn't a whole number whose square is 27. Okay, but we can factor this, right? Can you think of a factor of 27 that is a perfect square, right? So some perfect squares are what? So what are some perfect squares? Well, 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16, 5 squared is 25, and so on. So these all give you a correspondence, right? So the square root of 1 is 1, the square root of 4 is 2, the square root of 9 is 3, the square root of 16 is 4, the square root of 25 is 5, and so on. And I think you get the picture there, but you have this correspondence between squares and the square roots, and hopefully that makes sense with perfect squares. And similarly, you could write out a list for perfect cubes. Okay, but 27 has a factor That's one of these perfect squares here, right? It has a factor of 9. So we could write that as 9 times 3, and this as the square root of 9 times the square root of 3, and that is 3 square root of 3. So let's try to use the same pattern. Okay, now we want to take the cube root, right? So again, you could write out some perfect cubes. Right? 1 cube is 1, so the cube root of 1 is 1. 2 cubed is 8, so the cube root of 8 is 2, right? It's sort of the reverse process. And 3 cubed is 27. So the cube root of 27 is 3. 4 cubed is what? So 4 times 4 is 16. 16 times 4, 64, right? So the cube root of 64 would be 4, and so on. So if we want to take the cube root of 24, can we factor 24 as one of these perfect cubes? Well, yes, 24, we can rewrite this as what? Well, this can be written as the cube root of 8 times 3, right? And this can be written as the cube root of 8 times the cube root of 3. And the cube root of 8 is 2, and the cube root of 3, we'll just leave that alone. And so that would be the simplification for this one. So for our next one, we want to take the cube root of 162. And so what are the factors of 162? Now, if you don't immediately see that one of these perfect cubes is a factor, what you can, the factorization is actually unique. So what are some factors? Well, 2 is definitely a factor, right? So I could decompose this as 2 times what? So that would actually be 81. Now, 81 is not a perfect cube. However, what do you see? Well, I could decompose 81 a little bit more, and that's 2 times 3 times 27. And 27 is actually a perfect cube. So we can simplify a little bit, right? So we could decompose this as, well, you know what? Neither 2 or 3 have cube roots, so you could write this either as the cube root of 2, cube root of 3, cube root of 27, or you could actually leave these two combined together because, just write that as the cube root of 6, just because we're not going to be able to decompose it anymore. But it's up to you. So this is, it's really, they're both acceptable. That's what I mean. So this would be 3. So we could write this. It's usually a good idea to put the whole numbers in front of the roots. That's just sort of a standard thing to do because you can kind of think of those as the coefficients. And if you ever have like terms to combine in some kind of expression, it's a little bit easier to determine what are like terms. So this is acceptable, but you could also write that as the cube root of 6, like I was saying before, because we're not going to be able to decompose that anymore, as you can't factor that anymore into something that's a perfect cube, okay? I mean, 1 is a perfect cube, but that's a boring perfect cube, okay? So you're not going to need to do that. You'll just keep doing that forever. So moving on, we have to take the square root of 27 x to the 5th. So now we have some variables involved, and we can use many of the properties that we have seen before. So this would be what? Well, we could write this as 27. We can factor that as 9 times 2. And x to the 5th, you want to decompose that into something that is a perfect square. Well, x to the 4th should work out pretty well. And so should, you'll have a leftover x though, okay? Now, what do we have here? So, all right, you know what? if it's not clear that that's a perfect square, you could also write this as 9 times 2 times x squared times x squared times x. Okay? And then now this is, you know what, let me erase this. So what would this be? So you know what, let me write it under this actually. It might be easier to look at then. Okay. So this is the square root of 9, square root of 2, square root of x squared, square root of x squared, square root of x. So the square root of 9 is 3, square root of 2 stays the square root of 2, x squared. Now here's where you gotta be careful, right? This is actually absolute value of x, this is absolute value of x, and this is square root of x. So what you have is 3 square root of 2, quantity absolute value of x squared. Now, funny thing is, even if this thing was actually negative, okay, so this is an acceptable answer, but the funny thing is, if you happen to be plugging a negative into this, and you take the absolute value, you're making it positive, but then a square is always going to be non-negative. So actually, in this instance, you could actually simplify that to just x squared square root of x, and that would also be acceptable. Okay. However, if it was just x squared x by itself, you didn't have this extra one, you would have to leave that absolute value of x there, okay? So what do we have here? So now we have to take the cube root. So you want to decompose as best as you can into perfect cubes and then simplify, all right? So what is the factorization of 128? Well, we can just, if you don't see like a larger factor, you could start small, right? 2 is definitely a factor because the last digit is even. So I could write this as the cube root of 2 times what? What's half of this? Well, that's 64, right? And then x to the 6, we could write that as x cubed times x cubed, right? The sum of those exponents is x to the 6. Y squared, we'll leave that alone. You're not going to be able to write that as a cube, right? So now we have the cube root of 2. And isn't 64 a perfect cube? That was up on our list up above, right? So that's a cube root of 64. Cube root of x cubed, cube root of x cubed, and the cube root of y squared. So then that leaves this is done, this is done. So cube root of 2, this right here is what? That was 4, right? 4 times 4 is 16, 16 times 4 is 64. Cube root of x cubed is x. And since these are both odd, we don't have to put absolute values there. This is also x, and this is the cube root of y squared. So now we bring everything that isn't a cube root to the front. So this will be 4x times x times the cube root of 2 times the cube root of y squared. Okay, but this is actually the same as 4x squared cube root of 2 cube root of y squared. So that's acceptable, okay? So we could box that, but it might actually be better to leave this expression as 1 cube. So that would be 4x squared cube root of 2y squared. Okay, just combining these two together, all right? And that looks pretty good. So one other useful application of a lot of these properties is rationalizing. Okay, so rationalizing, you know, a rational is a ratio of integers. Okay, so rationalizing the denominator, we want to make the denominator best as we can. We want to get rid of the roots that are down here. Okay, now doesn't mean that we're going to end up with a rational number per se, but we are getting the roots to essentially be in the numerator, okay? And that'll make it so we can combine fractions and sort of have a standard form for a lot of our answers, and we want to check if we are correct, okay? Doesn't mean your answer would be wrong, it's just sort of standard procedure. Okay, so rationalize the denominator of the following expression. So if I have 3 divided by square root of 2, and I want to get rid of that root 2, the trick that we're going to use is we're going to multiply the numerator and denominator by root 2. Okay? Essentially what I'm doing right now, whoops, not 7, I'm multiplying by 1. Do you see that this is actually 1, right? Root 2 divided by 2, same thing, so that's 1. So what I'm doing is I'm just multiplying by 1 in a clever way. So I'm rewriting 1 as this ratio. And then now look at what we actually have. So the numerator multiplies, we have 3 root 2. And the bottom is the square of root 2. But what is that? The square of root 2 is actually just 2. Okay? And so here we see that what we end up with is a denominator that no longer has a root in it. Okay, and it is fully reduced, right? These coefficients don't have any common factors other than 1, right? Some non-trivial common factors to reduce. So this would be our answer. So the next example, we have 7 over root 5. We want to rationalize, so we want to get rid of the root 5 in the bottom. So how do we do that? Well, we can multiply by 1 in a clever way. So we're going to multiply by root 5 divided by root 5. And so we'll have 7 root 5. And then root 5 times root 5 is just 5. Okay? Root 5 squared. Okay. Well, what about our next example? So here we have a root of a ratio, and we had a problem up above, or a property that says that you could write that as the root of the numerator divided by the root of the denominator. So this is square root of 1 is 1, because 1 squared is 1, and root 3, we're going to leave that as root 3. But we want to rationalize this. So we want to get rid of the root 3 in the denominator. So we're going to multiply by root 3 divided by root 3. And so we'll have root 3 divided by root 3 times root 3, which is 3. So this would be our sort of standard answer when we are rationalizing.